Right, so now that we know what the Laplace transform is and the basics of how to compute it, we're going to talk about how to apply this information to ODEs. So this is 6.2, transforms of derivatives and ODEs. Right, so suppose you have a function f of t, and you want to find the Laplace transform of its derivative, f prime of t. Okay, well, to do that, we could set it up directly from the definition. This is the integral from 0 to infinity, e to the negative st, f prime of t, dt. Now that can be done by integration by parts. Well, first we should write this as a limit. This is the limit as b approaches infinity of the integral from 0 to b, e to the negative st, f prime of t, dt. Okay, now let's do integration by parts. Let's say u equals e to the negative st. In that case, dv is forced to be f prime of t dt. du is going to be negative s e to the negative st dt. And v is just going to be f of t. So this becomes the limit as b approaches infinity of uv, so e to the negative st times f of t, evaluated from 0 to b, minus the integral from 0 to b of v du, so that's going to be plus s e to the negative st times f of t dt. All right. So first of all, we can take this limit and break it up. We can turn this into the limit as b approaches infinity of e to the negative st, f of t, evaluated from t equals 0 up to t equals b, plus s times the improper integral from 0 to infinity of e to the negative st, f of t, dt. Okay, so what I've done here is I've distributed this limit among these two terms. I've factored out this s because it's a constant. And then the limit as b approaches infinity of the integral from 0 to b is just the improper integral from 0 to infinity. Okay, so let's continue. This is going to be the limit as b approaches infinity of e to the negative bs times f of b minus e to the 0 times f of 0. Plus s integral from 0 to infinity e to the negative st, f of t, dt. Okay, now as b approaches infinity, what does e to the negative bs times f of b approach? Well, I haven't made this clear so far, but it's a very minor detail. We're only going to consider functions where f of b times e to the negative bs, for s being greater than 0, approaches 0. Okay? We say that f is a function of exponential order. Okay? So we're only going to consider functions of exponential order to take their Laplace transforms in this class. Exception being, well, no. I was about to say there's an exception in the next lecture when we talk about the Dirac delta, but the Dirac delta is not a function. We'll get to it. Okay, but in any case, what I'm saying is this is going to approach 0. So what we get here is negative f of 0 plus s times this improper integral. But if you notice, this improper integral is exactly the same as the Laplace transform of f of t. So what this means for us is that the Laplace transform of f prime of t is equal to s times the Laplace transform of f of t minus f of 0. Okay. Now this is important because what we're going to want to do is take the Laplace transform of an ODE. And for an ODE, what we have is the derivative of some solution, but we don't know what the solution is a priori. So therefore, we're going to have to use this equation, this formula, to compute the derivative. So let's write this down on our big table of Laplace transforms, that the Laplace transform of a derivative, and by the way, this is also in the appendix at the end of my notes. This is s times the Laplace transform of the original function minus the original function evaluated at 0. And you can also compute that the Laplace transform of the second derivative, well, that's going to be s squared times the Laplace transform of the original function minus s times f of 0 minus s prime, or not s prime, minus f prime of 0. The Laplace transform of the third derivative is going to be s cubed Laplace transform of the original function minus s squared f of 0 minus s f prime of 0 minus f prime prime of 0. And so on. This pattern continues. And if you look at the appendix at the end of my notes, you'll see that I have the same information there. Okay, so how does this help us? Well, let's look at some examples of how we can solve ODEs using this information. So, example. What I want to do is solve the initial value problem, y prime prime plus 4y equals 2, with y of 0 being 3, and y prime of 0 being negative 1. We already know how to do that. We already know how to do that because we know the method of undetermined coefficients, and you can go through that whole process of finding the characteristic equation and finding the roots, and then, you know, everything that we did in the previous chapter. But this is just an example to illustrate how the method of Laplace transforms will work. So that's what we'll use, the method of Laplace transforms. So, we're going to take the Laplace transform of both sides of this equation. Laplace transform of y prime prime plus 4y equals Laplace transform of 2. Okay, then the Laplace transform is linear, so we can write this as the Laplace transform of y prime prime plus 4 times the Laplace transform of y equals the Laplace 2 times the Laplace transform of 1. Alright, great. Now, the Laplace transform of y prime prime is s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0. And we have all that information because we're dealing with an initial value problem. Okay. So what we get here is, first of all, this first term becomes s squared Laplace transform of y minus s times y of 0, so that's 3s, minus y prime of 0, so that's plus 1. Then add to this 4 times the Laplace transform of y equals 2 times the Laplace transform of 1. According to our table, the Laplace transform of 1 is 1 over s. Okay, so we have that. So now let's notice that we can factor a y out of the left-hand side and move everything else over to the right-hand side. So what we're going to do is we're going to write s squared y plus 4y equals 2 over s plus 3s minus 1. You can factor out a y and get s squared plus 4 times y equals 2 over s plus 3s minus 1. And then in that case, y is going to be 2 over s times s squared plus 4 plus 3s minus 1 divided by s squared plus 4. All right. So what does that give us? That gives us the Laplace transform of the solution y. So what do we need to do now? Well, if we can find the inverse Laplace transform of that, we'll be done. We'll have the solution y. Okay? So that's exactly what we'll do. We'll try to find the inverse Laplace transform of this thing. I'm going to do that on the other side of the board because this side is getting pretty cluttered and I don't want to erase this information. So 2 over s times s squared plus 4 plus 3s minus 1 over s squared plus 4. Right then. So we want to find the inverse Laplace transform of this. First of all, we can break up the second term into some more stuff. We can write this as plus 3s divided by s squared plus 4 minus 1 divided by s squared plus 4. And if you look at the table, you realize that we have some things on the right-hand side that look kind of like both of these. Okay? What we don't have is something that looks like this. So this is where partial fractions comes into play. We're going to do a partial fraction decomposition on 2 divided by s times s squared plus 4. In order to do that, we need to take a over s plus bs plus c divided by s squared plus 4. And then hopefully that will be something that we can more easily take the inverse Laplace transform of. So this becomes 2 equals a times s squared plus 4 plus bs plus c times s. You multiply through, you get 2 equals as squared plus 4a plus bs squared plus cs collect like terms in powers of s, and we have a plus b times s squared plus c times s to the first plus 4a times s to the 0. Now the powers of s are linearly independent functions. So therefore we can say the coefficients on the left are equal to the coefficients on the right. That means 0 equals a plus b, 0 equals c, and 2 equals 4a. That makes it pretty clear that a is going to be 1/2, and b is going to have to be negative 1/2. And meanwhile, c is 0. So what we get here is y equals, let's see here, 1/2 of 1 over s minus 1/2 of s over s squared plus 4 plus 3s over s squared plus 4 minus 1 over s squared plus 4. We have some like terms that we can combine. We can take 3 minus 1/2 is 5/2. So y equals 1/2 of 1 over s plus 5/2 s divided by s squared plus 4. I want to point out that 4 is 2 squared. And then minus 1 over s squared plus 2 squared. Okay, so now in order to find lowercase y, which is our solution, we just need to take the inverse Laplace transform of each of these terms. So we have 1/2 inverse Laplace transform of 1 over s. According to our table, that's just 1. So we have 1/2 times 1. Then add to this 5/2 inverse Laplace transform of s over s squared plus 2 squared. According to our table, that is cosine of 2t. Then minus, okay, we have 1 over s squared plus 2 squared. That doesn't exactly match up with 2 over s squared plus 2 squared. But that's okay, because all we need to do is multiply by 2 and 1/2 at the same time. So now we have 1/2 of inverse Laplace transform of 2 over s squared plus 2 squared is the sine of 2t. And then this is the solution of our initial value problem. Okay? So that's how the Laplace transform method works. You have an initial value problem. You take the Laplace transform of both sides. That gives you an equation that you can solve for the Laplace transform of the solution. And then your task is to find the inverse Laplace transform of that. And then you're done. Okay? So, of course, we're going to do another example. I'm going to erase this. So, let's suppose we have y prime prime minus 10y prime plus 9y equals 5t, y of 0 equals 0, and y prime of 0 equals 0. Let's try to solve this by the Laplace transform method. Again, we could have done this by the method of undetermined coefficients. That would have worked. But we're just doing it by the Laplace transform method in order to illustrate how this is done. So, you take the Laplace transform of both sides, y prime prime minus 10y prime plus 9y equals Laplace transform of 5t. Then the Laplace transform operator is linear, so we can get Laplace transform of y prime prime minus 10, Laplace transform of y prime plus 9, Laplace transform of y equals 5 Laplace transform of t. Okay, so Laplace transform of y prime prime, according to this, is going to be s squared times Laplace transform of y minus s times y of 0 minus y prime of 0. Thankfully, in this case, y of 0 and y prime of 0 are both 0. So therefore, we just have s squared times the Laplace transform of y. Minus 10 times Laplace transform of y prime, s times the Laplace transform of y minus 0. plus 9 times the Laplace transform of y equals 5 times the Laplace transform of t. Laplace transform of t to the 1 is 1 factorial divided by s to the 1 plus 1. So 1 over s squared. Now we have an equation that we can solve for capital Y, which is the Laplace transform of lowercase y, which is our solution. We can factor out capital Y from the left-hand side and get s squared minus 10s plus 9 capital Y equals 5 times 1 over s squared. In that case, y is equal to 5 divided by s squared times s squared minus 10s plus 9. Now, s squared minus 10s plus 9, that can factor into s minus 1, s minus 9. So this is the Laplace transform of our solution. And now here's the part where we take the inverse Laplace transform by partial fractions. We have to use partial fractions because, again, there's nothing on this table right here that looks quite like that. Okay? So, 5 over s squared times s minus 1 times s minus 9. This is going to be a over s plus b over s squared plus c over s minus 1 plus d over s minus 9. We multiply through, we get 5 equals a times s minus 1 times s minus 9 plus b times s minus 1 times s minus 9 plus c times s squared times s minus 9 plus d times s squared times s minus 1. We can distribute that. We'll get 5 equals a times, let's see, s minus 1 times s minus 9 is s squared minus 10s plus 9. Multiply that by another factor of s, and what you'll get is s cubed minus 10s squared plus 9s. Then we have b times s squared minus 10s plus 9. We have c times s cubed minus 9s squared. And d times s cubed minus s squared. All right. We can collect like terms in powers of s. Let's see here. We have a plus c plus d times s cubed, then plus negative 10a plus b minus 9c minus d times s squared, then plus 9a minus 10b times s plus 9b. The powers of S are linearly independent functions, so therefore we can set the coefficients on the left equal to the coefficients on the right. So 0 equals A plus C plus D. 0 equals negative 10A plus B minus 9C minus D. 0 equals 9A minus 10B. And 5 equals 9B. Okay. So, we have a system of 4 equations that we can solve for A, B, C, and D. First of all, it's pretty clear that B is going to have to be 5/9. In which case, A, well, we know that A is going to be 10 over 9 times B. So that's going to be 50 over 81. In order to solve the first 2 equations, or in order to solve for C and D, what I'm going to do is I'm going to add together these 2 equations. So we'll get 0 equals negative 9A plus B minus 8C, and then the D's cancel out. We already know that A is 50 over 81, so 0 equals negative 9 times 50 over 81. B is 5/9, so this is plus 5 over 9 minus 8C. That makes it clear that 8C is going to be negative 50 over 9 plus 5 over 9, which is just negative 45 over 9, otherwise known as negative 7. So then C has to be negative 7 over 8. Wait, no. 45 divided by 9, that would be negative 5. Sorry about that, folks. And minus 5 over 8. Okay. And then finally, the first equation implies that 50 over 81 minus 5 over 8 plus D is equal to 0. Let's see here. Finding a common denominator there is not easy, so you know what? I'm just going to write this as D equals 5 over 8 minus 50 over 81, and just leave it like that, because I'm already tired of doing this arithmetic. It's not the point, right? Okay, so I'm going to erase this part now because we no longer need it. capital Y is equal to, let's see, A is 50 over 81. Multiply that by 1 over S. Then B is 5 over 9. Multiply that by 1 over S squared. Then C is negative 5/8. Multiply that by 1 over S minus 1. And D is 5/8 minus 50 over 81. So 5/8 minus 50 over 81 times 1 over S minus 9. That is the simplest way of writing the Laplace transform of our solution. So now we just need the inverse Laplace transform. The inverse Laplace transform is going to be 50 over 81 times the inverse Laplace transform of 1 over S. That would be 1. Then plus 5 over 9 times the inverse Laplace transform of 1 over S squared. 1 over S squared is 1 factorial divided by S to the 1 plus 1, so that would be T to the 1. Then minus 5/8 S minus 1. 1 over S minus 1. 1 over S minus 1, its inverse Laplace transform is going to be e to the t. And then plus 5/8 minus 50 over 81, whatever that is. 1 over S minus 9. Inverse Laplace transform is e to the 9t. And that is at least one way of writing our solution to that initial value problem. Okay? Now, the advantage, as I mentioned before, of using the Laplace transform method is that it allows you to solve these initial value problems even when this inhomogeneous term might not be continuous, because we know how to take the Laplace transform of certain discontinuous functions, like the unit step function. So let's talk about an example where that happens. Let's start with something easy. Well, not easy, but simple. Y prime plus 9y equals u of t minus 1, where u is the unit step function, and y of 0 equals 1. So this is a first order ODE, and it's linear, but imagine trying to do this by... Actually, no, I just realized if you try to do this using the methods that we discussed for first order linear ODEs, that wouldn't actually be that hard. But let's do this by the Laplace transform method, just so that you can see how it's done. So Laplace transform of y prime plus 9y is Laplace transform of u of t minus 1. We have Laplace transform of y prime plus 9 times the Laplace transform of y equals the Laplace transform of u of t minus 1 by linearity. Okay, so then the Laplace transform of y prime, apparently that is s times the Laplace transform of y minus y of 0. Y of 0 is 1, so this is s Laplace transform of y minus 1 plus 9 Laplace transform of y equals Laplace transform of u of t minus 1. Well, I guess that would be e to the negative s divided by s. Okay. So now, what we have here is s plus 9 times y equals e to the negative s divided by s plus 1. Therefore, y, the Laplace transform of our solution, is e to the negative s divided by s times s plus 9 plus 1 over s plus 9. So now this can be easily handled. This one, on the other hand, is a bit harder. First of all, we're going to have to write it as e to the negative s times g of s plus 1 over s plus 9, where we're defining g of s as being 1 over s times s plus 9. You see, we're going to be using this seventh rule. The fact that e to the negative s times g of s, its inverse Laplace transform can be given by this. So first of all, we're going to have to find the inverse Laplace transform of capital G. In order to do that, we need to do a partial fraction decomposition. So this becomes a over s plus b over s plus 9 multiply through, you get 1 equals a times s plus 9 plus b times s. We get 1 equals a plus b times s plus 9a. Therefore, a plus b equals 0, 9a equals 1. We deduce that a is 1/9 and b is negative 1/9. So therefore, g of s, capital G of s, is 1/9, 1 over s, minus 1/9, 1 over s plus 9. And then we need the inverse Laplace transform of that. So that I'm going to call lowercase g of t. That will be 1/9 times 1 minus 1/9 of e to the negative 9t. And you can realize that by just looking at the table. Okay, so now we have g of t. According to rule 7, what we need is u of t minus a times g of t minus a, where in this case a is just 1. Okay. So we have y is going to be lowercase y is going to be u of t minus 1, g of t minus 1, plus then the inverse Laplace transform of 1 over s plus 9 is just e to the negative 9t. And then g of t minus 1, according to what we have over there, is, let's see, we have u of t minus 1, and then multiply this by 1/9 minus 1/9 e to the negative 9 times t minus 1. Then add to that e to the negative 9t, and that is the solution of our initial value problem. Okay, so as you can see, the Laplace transform method doesn't flinch in the face of having to deal with a non-continuous inhomogeneous term. And that's what makes it such an asset. So why don't we do one more example? This is one that we definitely couldn't do before today. So let's look at y prime prime minus y equals t minus 1 u of t minus 1. Y of 0 equals 1, y prime of 0 equals 1. We definitely couldn't solve this by undetermined coefficients, right? Because this inhomogeneous term is definitely not the right form to use the method of undetermined coefficients. So we have to use the Laplace transform method. So you take the Laplace transform of both sides. Laplace transform of y prime prime minus y equals Laplace transform of t minus 1, u of t minus 1. Then what we have here is, by linearity, Laplace transform of y prime prime minus Laplace transform of y equals Laplace transform of t minus 1, u of t minus 1. Okay, so Laplace transform of y prime prime, that's going to be s squared times the Laplace transform of y minus 1 times the Laplace times s minus 1 minus the Laplace transform of y. This equals the Laplace transform of t minus 1 times u of t minus 1. So let's take a look at our table. We have t minus 1, u of t minus 1. So let's understand that in this case, lowercase g of t minus 1 is just t minus 1. That means that g of t is just t. The Laplace transform of that, capital G of s, is going to be 1 over s squared. If you just look at the rule 2 in the table. Okay, so let's look at what rule 7 says we need to do with this. We need to have e to the negative 1s times g capital G of s. So e to the negative s times 1 over s squared Okay. So then this becomes s squared minus 1 times y equals e to the negative s times 1 over s squared plus s plus 1. In that case, y is going to be e to the negative s times 1 over s squared times s squared minus 1 plus s plus 1 divided by s squared minus 1. We get y equals e to the negative s 1 over s squared times s minus 1 times s plus 1 plus 1 over s minus 1, because the s plus 1's cancel out. So this one is easy. Let's not focus on it. Trying to find the inverse Laplace transform of it is easy. Let's not focus on this one. Let's focus on this one, because this one is harder. We have e to the negative s times a thing. Okay? What we're going to have to use is, again, rule 7. This time defining g of s as the thing that's multiplying by the exponential. So in this case, capital G of s is going to be 1 over s squared, s minus 1, s plus 1. And of course, we need to do partial fractions on this. So we have a over s plus b over s squared plus c over s minus 1 plus d over s plus 1. Multiply through, you get 1 equals a s, s minus 1, s plus 1, plus b, s minus 1, s plus 1, plus c, s squared, s plus 1, plus d, s squared, s minus 1. We can distribute everything and get 1 equals a times s minus 1, s plus 1 is s squared minus 1. So this is going to be s cubed minus s plus b times s squared minus 1 plus c times s cubed plus s squared plus d times s cubed minus s squared. Okay, then we combine like terms in powers of s. We have 1 equals a plus c plus d times s cubed plus b plus c minus d times s squared plus negative a times s minus b. From here, the coefficients on the left are equal to the coefficients on the right. So that means 0 equals a plus c plus d. 0 equals b plus c minus d. 0 equals negative a. And 1 equals negative b. Well, that makes it pretty clear that, first of all, A is 0, that B is -1, the first two equations therefore become C plus D equals 0, and C minus D equals 1. Add these two equations together, and you get 2C equals 1, therefore C equals 1/2. And then C plus D has to be 0, so that means that D is -1/2. Okay, so our capital G of S can be written as 0 over S minus 1 over S squared plus 1/2 of 1 over S minus 1 minus 1/2 of 1 over S plus 1. Okay, so we'll need the inverse Laplace transform of this, G of t. That's going to be, let's see here, -t plus 1/2 e to the t minus 1/2 e to the -t. So, y, lowercase y, our solution, is going to be, all right, we have e to the -s times g of s, so it should be u of t minus 1, g of t minus 1. So, u of t minus 1, g of t minus 1, plus e to the t. G of t minus 1, so we have u of t minus 1 times g of t minus 1 is -t minus 1 plus 1/2 e to the t minus 1 minus 1/2 e to the -t minus 1 plus e to the t. And that is at least one way of writing the solution of our initial value problem. Okay? So, that'll be all for today. It's already a pretty rough lecture, I think. But of course we will practice these and you'll get good at them. And I will see you in the next one.